Welcome to our deep dive today. We're going to be looking at Newtonian orbits. You sent over a really cool website. It has an interactive Kepler orbit simulation.
Oh, yeah, it's great. Even for people who don't know a ton about physics, they can get a feel for how objects move in space.
It seems like the website was designed for education. But today, we're going to kind of go beyond that, explore the concepts in a more fun way. For anyone who's curious about, space or physics.
Yeah, we can cover some of the basics of Newtonian mechanics, how they apply to orbits, and then we can also look at some of the cool aspects of the simulation, like how you can change the parameters and see what happens.
I'm excited to dive in. So the simulation focuses on Newtonian orbits. So that's how planets move around a star or how moons move around planets. It takes this complex 3D problem and makes it into a 1D problem. How'd they manage that?
So they use something called effective potential energy. You can think of it like a ball rolling on a hilly track. So the shape of the track, like the hills and valleys, that represents the potential energy landscape. And in the simulation, the orbiting object is like that ball.
I see.
And the effective potential energy, dictates how it moves.
So instead of the object moving in 3 dimensions, we're looking at its energy as it moves along this, one-dimensional track.
Exactly. And that's the trick to make the 3D problem of orbits into a 1D problem. It's so much easier to visualize that way.
Really cool. And I see in the source material that it mentions attracting and repelling forces. So it's not just gravity pulling things together. You can also make them push each other apart.
Yeah. And it really changes everything. Instead of the elliptical orbit we see with planets around the sun, with repelling forces, things might spiral outward or even fly away from each other.
Wow. So it really highlights how important attractive forces are for, the structure of the universe.
Exactly.
Okay, I have to admit, there's a term in here that intimidated me a little. Dimensionless variables. Can you unpack that for us?
Sure. So imagine you're building a scale model of the solar system, right? You don't need to use miles or kilometers. You could just say, 1 unit is the distance from the Earth to the sun.
Ah, okay.
Dimensionless variables are like that, a simplified set of units to make the calculations easier.
So it's like creating a mini universe with its own rules.
Exactly.
Yeah.
And it makes it easier to compare different orbits, and you can understand the ideas without getting bogged down in the numbers. So like instead of kilograms for mass, we use unit mass.
Makes sense. Is that kind of like how the simulation also uses a specific time unit?
Yeah,
Yeah.
exactly. It's like saying, in our mini universe, 1 tick of the clock represents this much time. It keeps things consistent.
Gotcha. That makes way more sense than like the formula they gave in the source material. Okay, there's one more term that caught my eye. I'm hoping you can help me with this one. Conserved Laplace-Runge-Lenz vector. What is that?
That's a really interesting one, and it's really important for understanding these Keplerian orbits. So imagine an object orbiting, right? As it moves, its position and velocity are constantly changing, right? But there's this vector, the Laplace-Runge-Lenz vector, that stays the same throughout the whole orbit.
Wait, so even though the object is moving all over the place, this vector doesn't change?
Nope. It stays constant.
What does that even tell us?
Well, it tells us a lot about the shape of the orbit. It tells us if it's going to be a circle or an ellipse, a parabola. It's like a code that tells us about the path the object is going to take.
So the simulation isn't just showing us the orbit. It's like giving us a glimpse into the math behind it.
Yeah, exactly. That's what's so cool about it. It connects that abstract math to the stuff we actually see happening in space. And there's more. The simulation actually lets you experiment. The activities section talks about how you can play around with things and see how they affect the orbit.
That's awesome.
Okay.
What can we actually do? Like, can we launch planets?
Well, not launch planets,
Yeah.
but you can change things. Like you can adjust the mechanical energy. Remember how we were talking about energy being conserved in a closed system? Well, you can tweak that here.
So you get to mess with the laws of physics.
Pretty much. And it's really cool to see what happens. Think back to that analogy with the ball on the track. What happens if you give the ball more energy?
It can go higher up the hills.
Exactly. So if you give a planet more energy, it's going to be able to move further away from the star.
Oh, so the orbit will change shape.
Yeah, it will become more elongated. You can see that happen right in the simulation. You can also change the initial polar distance.
What's that?
It's basically the starting position of the planet, like how far away from the star it begins.
Oh, so we can choose if it starts close to the star or further away.
Yep.
That must change the orbit too.
Oh, yeah. Big time. It's like choosing where you put the ball on the track. Where you start makes a huge difference in how it moves.
Okay, this is starting to sound really fun. What else can we play around with?
Well, Remember how we were talking about attracting and repelling forces? You can experiment with that too.
Yeah, that was really interesting. Seeing how different the orbits look depending on the forces. What should we look for when we're messing around with that?
You can really see how important those forces are. With attractive forces, like gravity, you get those nice repeating orbits, like circles or ellipses. But with repulsive forces, things can get wild.
Like how wild are we talking?
Objects could spiral outwards, or they might even just fly away from each other. Really fast, it's totally different.
Whoa. So it's like comparing a perfectly choreographed dance to a mosh pit.
That's a great way to put it. I think you'll really like that part of the simulation. And the source material actually suggests that you try to predict what will happen before you make the change.
Oh, so like make a hypothesis.
Yeah. It's a cool way to see if you understand what's going on. Does your mental model of how orbits work match up with what actually happens?
That's a fun challenge.
Yeah.
I like that they're encouraging us to think about it, not just click around.
Absolutely. They even suggest comparing the behavior of orbits under attracting and repelling forces.
I mean, we've talked about a little bit, but what are some specific things we can learn from that?
It really shows you how important attracting forces are. They create order and stability. With attracting forces, you get those nice, stable orbits. That's how our solar system works.
Planets orbiting the sun, moons orbiting planets.
Exactly. But with repelling forces, it's usually chaos. Things flying off in random directions. They might never come back. Attracting forces really are crucial for the universe we know.
Yeah. Without them, things would be a lot different.
Definitely. Simulations like this help us understand how things work. And they also help us appreciate how delicate the balance is, all these forces at play.
It's cool to think about. Those same laws and forces, they're everywhere. From planets and other galaxies to the satellites we launch, it's all connected.
And with these interactive simulations, it's so much easier to understand those connections in a way that's, visual and kind of intuitive.
It's like we can see the inner workings of the universe, all the forces shaping things around us.
And hopefully that sparks a little bit of wonder.
I'm definitely feeling that spark.
Yeah.
This has been a cool deep dive so far. But before we wrap up, there's one thing I wanted to ask. The source material mentions Newtonian gravity.
Yeah, Newtonian gravity, the model we've been talking about, super powerful, explains a lot about the universe, why things fall down, the way planets move.
It's like the gravity we experience every day, right?
Yeah.
Keeps our feet on the ground.
But it does have some limits. There are some situations where it doesn't quite work.
Oh, what do you mean? Like, where does Newtonian gravity break down?
Okay, so think about really massive objects, black holes, the gravity there is just insane. Or think about objects moving crazy fast, close to the speed of light. Newtonian gravity just doesn't cut it in those cases.
So you need a different model to understand those situations.
Right. That's where Einstein's theory of general relativity comes in. It's more accurate, especially in those extreme situations.
I've heard of general relativity. It's always seemed so complicated, though. Is there a simple way to explain how it's different from Newtonian gravity?
Okay, so imagine a bowling ball on a trampoline.
Okay.
It makes a dip, right? Like a curve in the surface. Well, general relativity says that massive objects do that to space-time. They warp it. And that warping is what we feel as gravity.
Whoa. Okay. So it's not that gravity is a force pulling things together. It's more like objects are just following the curves in space-time.
Yeah, that's a good way to think about it. And that curvature. It's much stronger around those really massive objects like black holes, or when things are moving super fast.
So Newtonian gravity is good for, the basics.
Yeah.
But when things get extreme, you need general relativity.
Exactly. It's like, imagine you have a map of a city, right? It's good for getting around. But then you find out there's this whole underground network of tunnels. General relativity is like those tunnels. A whole other layer of complexity.
That's a great analogy. So even though we focus on Newtonian gravity today, there's so much more to learn about gravity.
Always more to learn. That's the best part. The universe is full of mysteries, and it's our job to figure them out.
This deep dive has been amazing. We learned about Newtonian orbits, all sorts of complex ideas, and even a little bit about general relativity.
And we saw how interactive simulations can help us understand all this stuff.
Exactly. So to everyone listening, keep asking questions, keep exploring, and never lose that sense of wonder about the universe. Keep those questions coming, and maybe we'll deep dive into them in a future episode. Happy exploring, everyone!